Well, our final speaker today is Murad Alim, who will tell us about polynomial rings and topological strings.
Okay. Thanks for the introduction, and I would like to thank the organizers for letting me speak here, and also thank all of you for sticking around after a long day of interesting talks. So I'm going to talk today about joint work with Emanuel Scheidegger, who is in Freiburg, and Qingtung Yao and Jay Zhao, who are in Harvard, and actually Jay is right here. Okay, so let me start with a motivation for this work. So the reason we're all here is just that there's been fruitful interaction between mathematics and physics. So one particular line of thought that I want to highlight is that it's been very useful to think of physical theories in terms of families, so in terms of deformation families. In CFT theories, we're used to that from a long time. And in four-dimensional gauge theories, I would like to recall the Cyberking Witten exact solution of n equals 2 gauge theory, which they achieved by studying the theory together with its moduli space, or the space of inequivalent vacua. And every theory would correspond to some point in this moduli space. So they obtained an exact low-energy effective solution to this theory by identifying the moduli space of vacua with the moduli space of some elliptic curve. So we heard this story a couple of times at this conference before. So on the other hand, so this allowed physicists to sort of explore new ideas and think of gauge theories in a different context. But also the mathematics benefits from this translation of physics into mathematics, because then you can use the physics intuition and your knowledge about physical gauge theories to make new predictions of new structures and new equivalents in mathematics. So in particular, the idea of duality coming from physics is one that will be relevant in this talk. So by duality, I just mean that for n equals 2 theories, it's just an expansion, or it's just a different characterization of two members of the same deformation family of theories. The other thing is that many different, so completely different mathematical or geometrical setups often lead to the same physical theories. And hence, a physicist can say, well, okay, if you study this theory with this geometric setup, then it should be equivalent to another completely different geometric setup. And the most prominent example of this type of, well, duality, but it really is a symmetry, is mirror symmetry. So it identifies the moduli space of complex scalar forms of a Calabi-Yau threefold X with the complex structure moduli space of the mirror Calabi-Yau threefold Y. So this mirror symmetry will be implicit in all of the talk. And actually, it's these moduli spaces which will be the arena of things that will be happening in this talk. And there will be a particular instance of S-duality in sort of a non-gauge theory context, but just in a Calabi-Yau context. Okay, since it's late and the last coffee break is already over for a while, I'll start with giving you the punchline of the talk, just to make sure you get the take-home message. So what I want to talk about today is that these moduli spaces M, which are either the complex structure moduli spaces or the complex scalar, complexified scalar form moduli spaces, they admit the definition of an interesting differential ring structure. So I hope to convince you by the end of the talk also that the higher genus topological string amplitudes can be expressed as polynomials in the generators of these differential rings. And this is not something completely new, but it's a general story of some particular instances that most of you already know, namely for particular Calabi-Yau threefolds where the duality group sort of reduces to something nice that we already know. These polynomial rings reduce to the rings of quasi-modular forms. And at the end, I also want to show that in these cases, there's a very nice way to obtain sort of the dual information of these FGs just from using some mathematical involution. Okay, so I want to proceed by, sort of an extended introduction. So the goal of this is sort of to introduce the mindset of these polynomial rings using some structures that most of you will be very familiar with. So, but the goal is these structures are more general, and in some cases they reduce to something you already know. So I'll start by reviewing that. And one of these things has been reviewed this morning in the talk of Miranda. So it will be just a double review for you, so you know it more. Okay, so I'm going to start by recalling modular forms. So for tau in the upper half plane, recall that there is an action of SL2R on the upper half plane, sending tau to A tau plus B divided by C tau plus B. A modular form, as we learned this morning, or as you already know, is an holomorphic function which transforms in a very nice way if tau is sent to A tau plus B divided by C tau plus D, and ABCD is element in some subgroup of SL to Z. So the case most of us are familiar with is PSL to Z, which is generated by the two generators T and S. So T is sending tau to tau plus 1. In particular, this means for the modular forms that you can expand them in terms of a Fourier series. So you can use a variable Q, which is the exponent of tau. So this will be useful because, well, as we saw in Miranda's talk, most of these coefficients have some very nice interpretations, and manipulating modular forms will allow to make some very non-trivial statements. The other transformation, if we identify tau with the complexified coupling of some gauge theory, is the familiar S duality action. So unfortunately, or maybe fortunately, this type of duality only appears in n equals 4 theories where you have an exact electric magnetic duality. Because this transformation, so here on the right-hand side, I have drawn the upper half plane modded out by the PSL to Z group. So this gives you the fundamental domain, and there is one cusp at I infinity. And what this transformation is doing is exchanging the point at I infinity with 0, but they're exactly the same point. So, and this is the case for exact electric magnetic duality. Weak and strong coupling are exactly the same, up to potentially changing the gauge group to the Langlands dual. So this is not the story that appears in n equals 2 theories. Generically in n equals 2 theories, dualities are not exact, but they just refer to expansions of sort of different members of the same family of theories, but a priori they're completely different theories. And the sort of modular form manifestation of this is that the duality groups will be subgroups of PSL to Z. So the subgroups that will appear in this talk are gamma 0 n. So that's just matrices A, B, C, D, which are in PSL to Z, such that C is divisible by n. So here I've given two examples. Because they're subgroups, their fundamental domain is bigger. So here for gamma 0, 3, the fundamental domain is 4 times as big. And the interesting thing that happens is that there's a new cusp in this fundamental domain. So there is a new limiting point. And there is actually some involution which exchanges these two cusps. And if you know the modular forms and the action of the involution on the modular forms, then this will be exchanging really the expansion at two different points. And then after that, so also gamma 04 is here. So this will be the familiar case of Cyberking Witten theory, where the electric magnetic duality is not really a symmetry or some exact duality, but it's really also in the same spirit. It's exchanging the point at I infinity and the point at 0 using the same involution. Okay. So I want to proceed by introducing just the concept of rings of functions, which are sort of have nice properties. So I'll introduce a couple of modular forms in a rather unorthodox way. So I'll assume that you were given some modular form delta. So that's the Dedekind eta function to the 24, which appeared in the talk this morning, so which you get all over conformal field theories. So this is, you can show that this is a modular form of weight 12 of PSL to Z. So now just imagine, you can ask yourself what happens if I keep taking derivatives of this modular form. So the first thing I want to introduce, I'll just define a quantity E2, which I take to be the derivative of the log of this modular form. A priori, I don't know what this object is. But you can imagine that I can go on. So I can take the derivative of E2 and cast it in this form, which would define this object E4 for me. If I go on, then the next equation will define the object E6. And in the last step, something non-trivial happens, because there is a closure of this ring. So if I take a derivative of E6, then I will not generate anything new. So I'll start generating stuff that I already had. So it turns out, so another way of introducing these E2, E4, E6 is that these are the Eisenstein series of weight E2, E4, and 2, 4, and 6. And actually, E4 and E6 are modular forms of weight 4 and 6. But E2 is not quite a modular form. You need to introduce some non-holomorphicity in order to get a modular object. So this is called a quasi-modular form. So it is really the analogs of this ring that I'll be considering in this talk. So in some special cases, it will reduce to these rings, but more generally, it gives something more general where we don't know what the modular group is. Okay, so just a very brief review of the Cyberking Witten case. So I told you that this upper half plane modded by gamma 04 is the moduli space relevant for Cyberking Witten theory. So remember that Cyberking Witten, so a coordinate on the manifold of inequivalent vacua was given by the trace of phi squared, where phi is the adjoint scalar and the gauge multiplet. And well, the question was really, is it possible to obtain an exact answer for tau as a function of u? So tau being the physical coupling, in particular the imaginary part of tau, had to be positive definite. So this is a difficult answer. So in particular, this means, so there is no holomorphic way of getting this map, and this is why you have to allow some singularities in the U-plane, and these singularities will show up as cusps in this fundamental domain. So in order to solve the theory, there was some intermediate step. So the intermediate step was sort of, okay, instead of looking at this coordinate u on the moduli space and asking this question directly, let's introduce another set of, well, turns out to be sections of some bundle, but another set of coordinates A and A dual. And so when you're in the electric regime, you should use A as a physical coordinate. And when you're in the magnetic regime, you should use A dual as a physical coordinate. And by physical coordinate, I really mean that it gives the mass of BPS particle. And A is sort of attached to the electric part of the particle, and A dual is attached to the magnetic part. So just from knowing the leading singularities at different points in moduli space, Cyberking Witten were able to deduce the monodromy group of A and A dual, because some of these would have logarithmic singularities. And the monodromy group turns out, so in a particular choice of charges, to be gamma 04. And this whole problem mapped to the problem of studying, well, actually, tau that corresponds to some elliptic curve. So here it's the Cyberking-Witten curve in one of its many incarnations. So in particular, this way is convenient for, is in the spirit of talk of Andy Knightsky this morning. Okay, so let's move on. So the reason I introduced Cyberking-Witten theory and these modular forms is because, so I'm interested in the moduli spaces of Calabi-Yau's, but I like to think of these as sort of a generalization of this whole curve moduli space becomes the moduli space of a Calabi-Yau. So these people have shown that these theories, both in type 2b and type 2a, become some limits in non-compact threefolds. And so I'll consider just any Calabi-Yau threefolds. And the object I'm interested in is the topological string partition function. So if you want, so on the last slide, this tau would be computed as the derivative of A dual with respect to A, or the double derivative of something called the prepotential. And sort of what the topological string partition function is, you can think of it as some quantization of this moduli space and giving you a whole series of higher FGs. So where the lowest order just gives the classical, just gives the prepotential. So, and the coordinates on the moduli space, there will be also some T and some dual coordinate FT, which you should think of as the analogs of these Cyberking-Witten A and A dual. Okay, so let me review the special geometry of M. So this is the same spirit as you have some coordinates on M, and you want to compute the physical quantities, and there is some intermediate step, which in the Cyberking case was just figuring out A and A dual and how they change all over moduli space. So the analogous thing that you do in, to figure out quantities attached to the moduli space M is considering a bundle and how it varies as you move around M. So this holds for both the A side and the B side, but it will be more convenient to phrase everything in terms of the variation of complex structure. So you should think of this bundle as the Hodge bundle, and this will be the Hodge decomposition. So in particular, the data of the bundle will give you a Kähler potential for a Kähler metric on the moduli space. So e to the minus, so K is the Kähler potential, and omega is the holomorphic 3-0 form on the B side of the Calabi-Yau threefold. An additional object is the three-point function, or Yukawa coupling. That's a holomorphic object, and that's really sort of the target space manifestation of some ring structure that you have in a two-dimensional origin of these theories. So that's and actually, so that's the chiral ring of the 2,2 theory, which is at the origin of this, and the chiral ring structure constants, you see them if you take double derivatives. So this is sort of encoding how this whole bundle decomposition changes as you move around moduli space. Okay, so what is so this whole structure is then called special geometry. But what is special about special geometry? So phrased in terms of variation of Hodge structure, there is a flat Gauss-Manin connection. In physical terms, you can just use the fact that you have an additional ring structure to cook up some connection which is flat. And using the flatness of this Gauss-Manin connection, there's a particular form for the curvature that you can write down. So the nice thing about this curvature is that it combines this holomorphic three-point function with the anti-holomorphic three-point function. Otherwise, it's very simple. So for later use, I'll mention that this anti-holomorphic three-point function, you can locally write it as a derivative of some non-holomorphic potential for this. And having that, you can integrate this equation. So this will be of use later, this equation. So this just follows from the curvature expression if you remove di bar from all these quantities, and there is some ambiguity because you don't know, so from integrating the di bar derivative. Okay, so without going into much detail, Bershadsky, Chagorty, Egori, and Vafa, 20 years ago, by analyzing the two-dimensional origin of these topological string amplitudes, put forward a recursion equation, the holomorphic anomaly equation. So just to keep in, so without stating the details, where this comes from is contributions, so in perturbation on Riemann surfaces comes from contributions from the boundary of the moduli space of Riemann surfaces. So in particular, what I want to highlight here is that it's strictly recursive. So it gives you information about the higher genus, which are all expressed in terms of the lower genus amplitudes. So this type of equation started appearing in amplitude talks about n equals 4 theory, so it seems to be some fundamental structure of field theories or of string theories. Okay. So what BCUV furthermore did, so I told you that the non-holomorphic three-point function, I had already introduced this potential, but you can introduce further potentials. So you can think of this as the analog, the non-holomorphic analog of the pre-potential. So you can introduce some quantity such that if you take 3 derivatives, it gives you the non-holomorphic three-point function. And what BCUV showed that, okay, now you can go on and try to solve this equation recursively by just pulling out the I bars as much as you can, and then use the curvature expression or the commutator of di bar and d. And what they found is that actually at every genus, the amplitudes have an expression in terms of Feynman diagrams, which gives an in principle way to solve the theory genus by genus. So in principle, because it becomes very hard and the number of Feynman diagrams grows very crazy. And this situation improved a lot by work of Yamaguchi and Yao in 2004, which showed that for the quintic, actually everything that happens, or all the higher genus amplitudes, are just polynomials in a finite number of generators. So the reason this happens is that everything you have on the right-hand side will be derivatives acting on connections, and sort of everything is sort of in the realm of derivatives acting on quantities of special geometry. So that's the first sort of special geometry instance of the ring I want to talk about. And in work of mine with Dominic Lenger, we generalized the statement for any Calabi-Yau manifold. And what we showed is that actually the higher genus topological string amplitudes will be polynomials in exactly these potentials, or the propagators of the Feynman diagrams. And we gave some grading to these FGs. So just in principle, how we showed this statement, the first thing is that you have to show the closure, so much in the spirit as the ring of quasi-modular forms that I showed you. You have to show the closure of the ring of generators under derivatives. And then the second thing you can do just by induction. So these are the equations we found. So that's the closure of the ring of non-holomorphic generators. So everything in red is non-holomorphic, and all the blue quantities are some holomorphic functions, which in every case turned out to be rational functions in the moduli. And the induction step just starts by writing down the genus 1 amplitude in the generators, and then seeing or showing that the holomorphic anomaly can be recast in some polynomial form. So it just becomes a polynomial recursion in these generators. Okay, so what we did new in this work is sort of try to figure out a particular convenient set of coordinates on the moduli space and a particular choice of these generators, which would give us the quasi-modular forms on the nose for the cases where we would expect to see them. And for the other cases, would just give some potential candidates for the analogous structure that we don't know. Okay, so the first thing is, so here I'm just introducing the special coordinates. So one way to think about these, so these would be the physical coordinates, which are common to both sides of mirror symmetry. On the B side, these arise from the periods of the holomorphic 3 form. So in particular, a normalized version of the holomorphic 3 form will have the expansion where some of the periods will be the TA coordinates, and the dual periods will be the F, the derivatives of the prepotential, which I want to motivate as the dual coordinates. Okay, so the coordinate, yet another coordinate that we chose, is tau. So this is really the analog of the tau that would be sort of the gauge coupling of the Cyberking-Witten theory if you would have taken the Calabi-Yau, which gives you Cyberking-Witten theory. So tau would be a double derivative of the prepotential in general in the general case. So the generators we took, so first we translated everything into the special physical coordinates, and then translated everything into the tau coordinates. And we picked some particular choice of generators. And the nice thing, so this is the analogous ring, which now has some more holomorphic generators, but now captures everything. It captures everything, and you don't have to go through all these generators, but the one nice feature about this is that you can assign a strict grading to all of the generators. So the grading is given by the subscript. So this grading will coincide with the modular weight. But in general, we don't know what is the modular weight because we don't know the modular forms except for some tiny subset of the Calabi-Yau geometries that we're looking at. But the ring nevertheless has the grading, and it obeys that this grading is strict in the sense that the tau derivative increases by 2. Okay, so let me give you an example. So we revisited a much-studied case of local P2. And so this is the ring of generators. So because it's a non-compact Calabi-Yau, sort of most of what's happening here is becoming easier. Most of these generators, you can choose them to be 0. And the only thing that happens is sort of you have a non-holomorphic generator, a generator of rational functions, and some additional holomorphic generator here. And we can translate all of these generators into known quasi-modular forms. So we knew that E2 was a quasi-modular form for PSL2Z, and this combination is the analog for gamma 0, gamma 03. Likewise, these are all nice quasi-modular forms for gamma 03. So we did this for a whole other bunch of local Del Pezzo geometries where you would get other gamma 0 n groups. So yeah, so here just showing that the genus 1 amplitude and the genus 2 amplitude can be expressed in these generators. And then one nice feature, I told you about this freaky involution which exchanges the two cusps. And there is an action of this involution which tells you how the quasi-modular forms transform. So the relevant transformation in this case is just that what we chose to be the generator of rational functions gets inverted. So what you can do with this, you can just take the expression you have at any genus and do this involution and then expand. And the expansion would be the expansion that you have at the other cusp. So the other cusp turns out for Calabi-Yau manifolds, it's an exchange. So the two cusps are the large complex structure and the conifold locus. So you get in a very simple step, if you have the expansion in one patch in moduli space, very simply you get it in a different patch. But you still have to figure out how to expand it in terms of the physical coordinate and not in terms of tau. Likewise, in Cyberking Witten, you had to figure out A and A dual because nothing physical was expressed, well, apart from the coupling. The masses and so on were not expressed in tau. Okay, so just to end, well, we could do the same thing for the quintic, and this is so some choice of this ring. And in principle, so far we have only done this for one-dimensional moduli spaces, but we can write down the analogous rings. So, and we expect that this ring should really be the analog of the ring of quasi-modular forms for any other Calabi-Yau manifold and for any other duality group. Okay, so let me summarize. I showed you that there is a differential ring structure constructed using just the special geometry of the moduli space of a Calabi-Yau threefold, and that in some, well, we can choose some particular generators of this ring and a particular set of coordinates such that this whole thing coincides with quasi-modular forms for some particular cases, but gives something new otherwise. This ring had a nice grading. Moreover, the FGs, I haven't showed you this, but it's easy to show, are of degree 0 in these polynomials, in these generators, which means that there will be, generically, there will be just ratios of generators. And whatever appears in the denominator will know about the singularities of this theory. Okay, as an outlook, yeah, so as I said, for the most general case, we don't know what the ring of quasi-modular forms is, but this construction gives a candidate for these guys. Another thing would be interesting to study is what is the interpretation of this tau coordinate in general. So the tau coordinate in the cases which reduce to gauge theories where we know it had an independent mathematical meaning, being the flat coordinate of some variation of Hodge structure on a curve inside, which sort of inside the Calabi-Yau threefold. So the question is whether the tau also has an interpretation for the quintic, for example, as being the flat coordinate of some variation of Hodge structure which sits inside the bigger variation. So in particular, as we learned from Miranda's talk, it's almost surprising if a modular form or the analog of modular form expansion does not have a enumerative interpretation. And of course, so there's a lot of integrality here. So another question is, what is the enumerative interpretation of this Q tau expansion, or just so in the general case, but also for the cases where we know that it reduces to quasi modular forms. Okay, that's where I want to stop. I want to thank my collaborators and thank you all for your attention.
All right, so any questions?
So in the case where you have more than one dimension, so I guess you get more than one tau. So.
Yeah, so tau in general will be a matrix. So we're working on figuring out, so what you would have to figure out is what is a local one-to-one map between the flat coordinates and which entries of the matrix. Yeah.
Any more questions?
Can you talk about generalized homomorphic equation?
You mean refinement in terms? Yeah, I didn't talk about. Yeah, but I think there's work by Albrecht Klemm and Minjin Huang. So it doesn't change. It doesn't. The fact that sort of genus by genus, or then maybe epsilon. So all the epsilon 1, epsilon 2 terms should also have some quasi-modular interpretation. And I think so. This is largely done in cases which reduce to gauge theories anyhow. So it's probably more likely that in these cases we will recover known quasi-modular forms. So I don't think it's possible for the compact Calabi-Gauss, so for quinting, but I don't know too much about that.
Okay, another question.
Apart from the snowfall models and the quintic, did you try any other, for example?
There's no obstruction in doing so. So yeah, so you could in principle. It's not hard to figure out what the ring is. So we just have the general construction. And we just did one compact example just to show how it works concretely.
Any more questions? All right, if not, let's thank Murad again.